Okay, calculus, we are on day 6 of curve sketching, and we're going to do a curve sketching algorithm. It's not the final algorithm, but it's certainly going to get us there. This is close to page 192. I just kind of abbreviated the bottom section, but we're going to go step by step so that we really got an organized structure for coming up with key pieces, helpful pieces to help us curve sketch. So step number 1 is to check for any discontinuities in the domain and see if you have a vertical asymptote or not. So first example, we're going to keep flashing back to the screen, is this function. So step number 1, I've got myself completely tangled here. Okay, looking for number 1. We are looking for discontinuities in the domain. So my discontinuities, the one and only discontinuity is x equals 5. So it's either a hole or it's an asymptote. So I'm going to see, just because I find this the easiest way, is to see if I can factor it. If it's factorable and therefore a hole, then I can do that. All right, let's see. X and X, if I have a 5, if I have a 3, it would have to be positive. If I check with FOIL, it's good to go. Therefore, because I can do that, it is a hole, not an asymptote. So in my list of things to do, I have shown that I thought about it. I have a hole. I'm going to keep that in mind when I make my curve. Number 2. Is find the y-intercepts and the zeros, just because they're such key points and so helpful in curve sketching. So I want y-intercept and x-intercepts or zeros. So for this particular one, for my y-intercept, that's when x is 0. So I have negative 15 over negative 5. And so I have the point 0.03 for my y-intercept. For my x-intercepts, my function is 0, which we looked at already. That happens when x is negative 3. So for my x-intercept, I have the point negative 3, 0. All right then, let's look again. Step number 3, find any critical points and determine where the curve is increasing and decreasing. So I combine step 3 and step 4 so that as I am organizing my thoughts, I am looking for increasing and decreasing, which will tell me whether I have a max or a min. So when I organize that table that I make you do, then we have done steps 3 and 4 together. All right. For this particular function, we are looking at the first derivative test. So I want to look at f prime x. Here we go. So I have a quotient. So I am going to do the derivative of the top. 2x subtract 2 times the bottom. Subtract the top. 2x negative 15 times the derivative of the bottom, which is what? All over the bottom squared. Let's tidy this up a little bit. I have 2x squared, negative 10, negative 2, negative 12x, plus 10, subtract x squared, plus 2x plus 15. Whoop. What do we get here? I think I've made this more painful than I needed to, but that's okay. Plus 25 over x subtract 5 squared. What do you know? I have x subtract 5 squared over x subtract 5 squared, which is 1. The derivative is never 0. It is always positive. It is always increasing. Interesting. All right, was there anything else I needed to look at in my algorithm? So steps 3 and 4, there weren't maximums and minimums. This thing is always increasing. We want to look at the extremity tests. This is an interesting one. Okay, let's look at, where are we, number 5. So we are looking at the limit as x approaches infinity. I'm going to divide out the largest power of the top and the bottom. Now I know you're looking at it and you're saying the degree of the top is 1 larger than the bottom. It should have an oblique asymptote. Let's just do this my way for a second. So if I divide x squared into x squared negative 2x negative 15, I have 1 negative 2 over x negative 15 over x squared. Over. I'm going to divide a power into the denominator of x, which would give me 1 subtract 5 over x. All of these fractions get closer and closer to 0. I end up with x over 1 times 1, which is the limit as x approaches infinity of x when all the smoke clears, or negative infinity, which would give me infinity or negative infinity as we go to the right and to the left. That's just crazy. So what we have is this function that is an oblique line, looks like an oblique line with a hole in it at 5, 2, 3, 4, 5, about right there. And this thing is itself an oblique asymptote that looks like x plus 3. So yes, I guess technically it has an oblique asymptote, but this is what we're looking at because it divides in evenly. Cool. Let's do the next one. F at x equals x squared plus 3x plus 7 over x plus 2. So step number 1 is to look for discontinuities. Our discontinuities happen at x equals negative 2. Is it a whole or is it an asymptote? So if I try and factor this thing, I would try to do x plus 2 times x 2 times, nada, not going to happen. That's going to be an asymptote. I'd like to know what it's doing to the left and to the right just by doing some quick values. So for my asymptote, actually I should write that down. That's my vertical asymptote. Oh man, I can't even spell today. Today you say. Asymptote. Okay, I'm just going to look a little to the right, a little to the left, sorry, a little to the right, and see what's going on. So a little to the left, I get a value about negative 51. And a little to the right, I get a value of negative 49.1. So for my asymptote at negative 2, as I approach from the left, I'm going down. As I approach from the right, I'm going up. And that's all I got so far. Step number 2 is to look for intercepts if possible. Intercepts, y-intercept and zeros. Okay. For my y-intercept, if I put a 0 in there, I get 7 over 2. I get 3.5. 0, 3.5. All right. My x-intercept. This is where the function is 0. specifically the numerator, I would use the quadratic formula for this one. -3 plus or minus 9 minus 4ac. Oh no, we just have complex roots, which technically we are not going to have any x-intercepts. No x-intercepts. So we got that guy. That's it. Number 3 and 4. We are going to do the first derivative test by finding our critical points and determining if they're maximum and minimums in the interval. So we need to look at the derivative and see when it is 0 or undefined. So my derivative is going to be, all right, we got a quotient again. Derivative of the first times the second. Subtract the first derivative of the second, which just happens to be 1. All over the second squared. Okay, I'm going to tidy up. You go, I go. 2x squared over 7x plus 6. Okay, subtract x squared, subtract 3x, subtract 7. All right. Because I want to know where this thing is 0, I'm going to just tidy another step. I have x squared plus 4x minus 1 over x plus 2 squared. Okay. We are looking for the derivative to be 0 or undefined. We've already talked about x equals -2, and we already know that there is an asymptote there. So I don't need to spend time looking at that place, but I do need to see where it's 0. X squared plus 4x subtract 1. All right, so again, we are looking at the quadratic formula to find those critical points. So we have -4 plus or minus the square root of b squared minus 4ac over 2a plus or minus root 20 over 2, which is approximately decimal 24, or approximately -4.24. So these are our critical points. And the first derivative test would say, tell us what those are. And I find it just awesome. Are you taking my hint? To set up a little table so it's really clear to everybody what's going on. So we know we have a little funky business about -2, but we're going to ignore that in this table. We're going to look at the two places, -4.24 and 0.24. Those are both zeros in our derivative. So I want to look to the left. I want to look at the interval in between. 4.24, sorry, I've got an extra decimal in there. At 0.24 and greater than 0.24. Okay, so I'm using my derivative. I just need to have it a little closer. There we are. I am putting values there, to the left and to the right. So I am going to put a value of -5 in there. So I get 25, subtract 20, subtract 1 is positive on the top, positive on the bottom. I'm going to put a value between -4.24 and 0.24. I am going to put a 0 in there, and I will get -1 over 4, so negative there. Greater than 0.24, I'm going to put a 1. 1 plus 4 is 5 is positive, positive. So I get positive here. That tells me about my function, knowing that there's a little funny business going on at -2, but I have increasing, I have decreasing, so this must be a maximum. I have decreasing, I have increasing, so this must be a minimum. Step number 5 asks us to look at the end behavior. Just flash back here for a second. Okay, step number 5. Extremity tests, we're looking for a limit as x approaches infinity and -infinity for horizontal and oblique asymptotes. Here we go. So for this one, for a horizontal asymptote, we would look at horizontal. Okay, the limit as x approaches infinity. I'm going to factor out the largest power of the variable, so x squared for the top, x for the bottom, 1 plus 3 over x, plus 7 over x squared for the bottom. If I factor out x, 2 over x, we know that those fractions over x approach 0 as x gets really, really large. I know that this cancels that. If I divide out x, it approaches infinity, or the limit as x approaches -infinity would be -infinity for the function story. So there is no horizontal asymptote. This would be a really good way to show that. Another would be to discuss the fact that you can't have a horizontal and an oblique asymptote at the same time. And this one has an oblique asymptote, but don't just gloss over it. Make sure you tell me that. For the oblique asymptote, because it is 1 degree higher in the numerator than the denominator. Asymptote. Okay, numerator. Here we go. We are going to rewrite our function in a different look by using long division. So if I take the denominator and divide it into the numerator, I can change form. So this is fun. Red for danger. X, so I'm just looking at the first part. X goes into x squared, x times. X times x plus 2 is actually x squared plus 2x. All right then. I'm going to subtract first line from the second line. If you do x squared, subtract x squared, disappear. 3x subtract 2x is x. I'm going to bring down that 7 so I don't forget about it. How many times does x, again, go into x plus 7? It goes in 1 time. 1 times x plus 2 is x plus 2. So we are going to have a remainder of 5 x plus 2's. So I can rewrite my function as x plus 1 plus positive 5, right? Plus 5x plus 2's. So that is the same as f at x. And now I can clearly see that my oblique asymptote would be x plus 1, because this fraction approaches 0. Again, you don't have to write that every time, but approaches 0 as x gets very, very large. So this is my oblique asymptote at x plus 1. Let's draw it. So I have already, yes, I have my vertical asymptote already. I have an oblique asymptote at x plus 1. plus 1. Okay. I need a couple key points really. Let's make sure, I just need some space at the end. I have my intercepts, I have my asymptotes. I would like to add to the pile my critical points. So I'm just key points. My critical points would be at 0.24 and at negative 4.24, which is where I have a maximum and a minimum. My 0.24 value is 3.47. And my maximum is negative 5.47. This seems counterintuitive, but let's put them on at negative 4.24. 1, 2, 3, 4. I am at negative 5.47. Okay, so I did a funny little job here with the, there we go, the asymptote, because that is in fact a maximum, which did seem backwards, but I have got, I'm approaching this asymptote. There's my maximum in the interval, and then it decreases this way. So maximum overall, not so much. But a maximum in the interval, absolutely. So 0.24 has a value of 3.47. 1, 2, 3.47, which is a minimum, whoops, which is a minimum in the interval. And we approach the asymptote here and there. Messy but true. We have our function. We should check that on Desmos.